Okay, so this is the setup I'm going to be using. You'll notice this side there's like a blanking insert that goes into the bearing housing on this side, and on this side you attach the motor, so the hole is empty, just with the spindle sticking through. So I quickly realised that when I spun this thing up, due to the presence of material here and the absence of material here, there was a weight imbalance. So I contacted the manufacturer and asked them if this is expected, and they confirmed it was and offered to make me a one-off insert to go in here for free. But they also suggested that what I could do is use some Play-Doh, some kids' plasticine. So I did that. I got some of my daughter's Play-Doh, just spun it up to speed with the motor and then inserted this into the hole. That seemed to do the trick. I was able to balance it perfectly. Before I put this in, the extra weight caused this side to drop every time, and if it was over here it would drop this way. So that's how I overcame that. I've attached the whole setup to a protractor which I've blue tacked to the table, and I've blue tacked the actual the frame to the table as well. So this here is the angle that we're looking for. So what we're looking for is this effect. See how the gyro wants to rotate and stay in the original orientation? Well, that angle that it's rotating, that this bar appears to be rotating over the vise, that is the angle that we're looking for. That is the angle that we should be able to calculate this gyroscope moving due to the rotation of the earth underneath us. So without further ado, let's get on to the test. So I've just attached the motor there. It actually takes 4 AA batteries to power it, and I've run this test quite a number of times now and put quite a few batteries through it, so I kind of know how long they're going to last and what sort of sound comes from the motor, depending on how much power is left in the batteries. And I'd say there's about probably 75% power left in them at the minute, and that's based on 12,000 RPM maximum. That's probably about 8,000 or 9,000 RPM for this particular test. So it's getting up to speed now. I'm going to remove the motor and replace it with the piece of Play-Doh to get it perfectly balanced. And now I'm going to demonstrate some precession by gently pressing on the horizontal bar there. And now I'm going to line it up as best I can, so that you cannot see the brass flywheel from above, and it's as sort of straight up and down as possible. So if we just take note of where we are now, at you can see a 0 on the top right, just to the right of the bar. You can see a 0 just there, and you'll note that you cannot see the brass flywheel from above now. So we are sort of dead centre above it. So now it's just a waiting game. So while we wait, let's just have a look at a brief history of the gyroscope, up to the point where it was first proposed that it could record the spin of the Earth. So this is just sort of one example that I found on the internet. There are lots and lots of different accounts and they all differ slightly, but this one seemed like a sort of all-round recount of history. So in early times, people discovered the spinning top, a toy with a unique ability to balance upright while rotating rapidly. Ancient Greek, Chinese and Roman societies built tops for games and entertainment. The Maori in New Zealand have used humming tops with specially crafted holes in mourning ceremonies. In 14th century England, some villagers had a large top constructed for a warming up exercise in cold weather. Tops were even used in place of dice. It was not until the late 18th and 19th centuries that scientists and sailors began attempting to use spinning tops as a scientific tool. At the time, sailors relied on sextants for navigation, measuring the angle between specific stars and the horizon. This method was limited, however, if choppy seas or fog obscured the true horizon, or clouds obscured the stars. Serson, an English scientist, noted in the 1740s that the spinning top had a tendency to remain level, even when the surface on which it rested was tilting. He suggested that sailors could use it as an artificial horizon on ships. Unfortunately, when Serson went to sea to test the idea, the ship sank and everyone was lost. A French scientist in the 19th century, Fleury, created a top that was continuously powered by air jets, blowing into mini buckets on the rim of the wheel, a process that had been used for thousands of gyros since. The first modern gyroscope was designed in the early 1800s by Johann Gottlieb Friedrich von Bernberger, a professor at the University of Tübingen in Germany. It was made with a heavy ball instead of a wheel, but since it had no scientific application, it faded into history. In the mid-19th century, the spinning top acquired the name gyroscope, though not through its use as a navigational tool. French scientist Léon Foucault had experimented with a long, heavy pendulum in an attempt to observe the rotation of the Earth. The pendulum was set swinging back and forth along the north-south plane, while the Earth turned beneath it. Foucault corroborated the observation by using a spinning top in a similar manner. He placed a wheel, rotating at high speed, in a supporting ring in such a way that the axis of the spinning wheel could move independently of the ring. In fact, the supporting ring moved over the course of a day, as it was connected to the surface of the rotating Earth. The axis of the wheel remained pointed in its original direction, confirming that the Earth was rotating in a 24-hour period. Foucault named his spinning wheel a gyroscope, from the Greek words gyros, which is revolution, and skopin, which is to see. He had seen the revolution of the Earth with his gyroscope. So, from Wikipedia, Jean-Bernard Léon Foucault, born 18th of September 1819, was a French physicist best known for his demonstration of the Foucault pendulum, a device demonstrating the effect of the Earth's rotation. He also made an early measurement of the speed of light, discovered eddy currents, and is credited with naming the gyroscope, although he did not invent it. Foucault was the son of a publisher in Paris, where he was born. After an education received chiefly at home, he studied medicine, which he had abandoned in favour of physics due to a blood phobia. He first directed his attention to the improvement of Louis Daguerre's photographic processes. For 3 years he was experimental assistant to Alfred Donné in his course of lectures on microscopic anatomy. In 1851 he provided an experimental demonstration of the rotation of Earth on its axis and became well known to the public by Foucault's work. Foucault achieved the demonstration by showing the rotation of the plane of oscillation of a long and heavy pendulum suspended from the roof of the Pantheon in Paris. The experiment caused a sensation in both the learned and popular worlds, and Foucault pendulums were suspended in major cities across Europe and America, attracting large crowds. In the following year, he used and named the gyroscope as conceptually simpler experimental proof. In 1855 he received the Copley Medal of the Royal Society for his very remarkable experimental researches. In 1862 Foucault was made a member of the Bureau de Longitudes and an officer at the Legion of Honour. He became a member of the Royal Society of London in 1864 and a member of the mechanical section of the Institute a year later. He is also credited with determining the speed of light to be 298,000 km per second, which is only 0.6% in error of the currently accepted value, and devising a method of testing the mirror of a reflecting telescope to determine its shape. So, reading between the lines, he was a man of significant academic accomplishment and recognition at the time. One has to wonder then why, when you read the Wikipedia article about Léon Foucault, does it have this one line at the end? Near his death, he returned to Roman Catholicism that he had previously abandoned. Draw your own conclusions. So going back to the test, we've exceeded 6 minutes now and there's no observable movement. You can still see the zero to the right of the bar in its entirety, and you still cannot see the brass fly